Okay, hello everyone. In a new video. In this one, we are going to solve an exercise related to mechanics and the chapter of pressure and liquid. This exercise was the previous one in the brevet exams in 2018 second session, third exercise. The title of this exercise is Pressure of a Confined Gas. The object of this exercise is to determine the pressure of a confined gas. For this, we consider a glass bulb having a closed tap R and filled with gas. A rubber tube connects the glass to a U-tube manometer. This manometer contains water in equilibrium. The surfaces of water in the two branches are at the same level. So given that the atmospheric pressure is equal to 76 centimeter of mercury, so notice that here the quantity and the unit are not in agreement, because we know that the SI unit of the pressure is given by Pascal or Newton per meter square. So from the early beginning we need to rewrite this given properly. So centimeter is the unit of length or depth in particular. So this value 76 centimeter correspond to the atmospheric height that is used to calculate the atmospheric pressure. So notice that here centimeter is not the SI unit of length. In order to convert from centimeter to meter, we simply divide by 100. Then 76 divided by 100. Then the atmospheric height is given by 0.76 meters. And the density of mercury is given by rho 1 is equal to 13,600 kilogram per meter cube. And the density of water is given by 1000 kilogram per meter cube. And the G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Now we open the tap R. We notice that at equilibrium the difference in levels between the surfaces of water is 10 centimeter. See the figure. So here first let me write that. Okay, let's denote this 10 centimeter to be H. Knowing that centimeter is not the SI unit of length or depth, in order to convert from centimeter to meters, we simply divide by 100. So this height is given by 0.1 meter. So what's happening here is that we open the tap R. So here this tap allows the confined gas to pass from this glass pulp to the U-tube. So previously this manometer, which is the U-tube, contains water in equilibrium, and the surfaces of water in the two branches are at the same level. So before opening the tap R, the water in equilibrium in the two branches is in the same horizontal level like this. The moment we open the tap R, this confined gas will exert the pressure at the point B. Therefore the point A, which was previously in the same horizontal level at B, will rises. Then the difference between the point B and A is given by 10 centimeter. Now number 1, determine in Pascal the value of the pressure exerted by air at A. So we are interested in determining the pressure at the point A. So whenever we are determining the pressure, we always look upward. So notice that the point A is open to the atmosphere, then A is submitted to the atmospheric pressure, which is this case given by the pressure exerted by air. So they usually give half a mark for this statement. Now the pressure at the point A, which is equal to the atmospheric pressure, the atmospheric pressure is equal to the pressure exerted by 76 centimeter column height of mercury. So it's the pressure due to the liquid, which is given by the density of the liquid times G times H. Now this liquid is mercury, so its density is given by rho 1 times G times 76 centimeter, which is the atmospheric height. Now the density of mercury is given by 13,600, and the value of G is given by 10. and the value of the atmospheric height is given by 76 centimeter in this case. And the SI 0.76. Now plugging this on the calculator, then the atmospheric pressure is given by 360 Newton per meter square. And another unit for a Newton per meter square is given by Pascal. Then the atmospheric pressure at the point A is given by 103,360 Pascal. Now number 2, calculate the value of the pressure exerted by water at sea. So notice that here C, okay, we are interested in determining the pressure, so we always look upwards. C is submitted to the pressure of this liquid and to the atmospheric pressure. They are telling me to calculate the value of the pressure exerted by water at sea. So let's denote this pressure by PW, and it's the pressure due to a liquid which is given by the density of the liquid times the G times the depth at which we are calculating this pressure. The density of this liquid is given by water, which is ρ2, times G times the depth or the height at which we are calculating the pressure, which is given by H. The density of this liquid is given by 1000 times the G, which is 10, times H, which is 0.1. Plugging this fraction on the plugging this on the calculator, then the value of the pressure of water is given by 1000. Since everything is expressed in the SI, so the value of the pressure will be expressed in the SI, which is given by Newton per meter square. And another unit for Newton per meter square is Pascal. So the pressure exerted by water at the point C is given by 1000 Pascal. Now number 3, deduce the value of the total pressure at sea, and by deduce it means that we need to use the previous part. In the previous part we have determined the pressure exerted by water at the point C, and previously also we have determined the atmospheric pressure. So we are interested in determining the pressure at the point C, so always look upward. It's being submitted to the pressure of this liquid and to the atmospheric pressure. Then let's say C is submitted to the pressure of water, so the liquid in this case is water, and to the atmospheric pressure. So pressure at point C is equal to pressure due to water plus the atmospheric pressure. The pressure due to water is given by 1000 plus the pressure at the point A is given by 103,360. So the total pressure at the point C. Now plugging these values on the calculator. So the pressure at the point C is given by 104,360. Since both this and this are expressed in the SI, which is given by Pascal, so the value of the total pressure at the point C is expressed in Pascal as well. Now as for number 4, part A, B and C are under the same pressure Y, so all such type of questions are answered using the rule of 3, which is given by same liquid at equilibrium, and either we say same pressure or same horizontal level. Since we are interested in justifying why they have the same pressure, so we will eliminate this, and our answer will be they are in the same liquid at equilibrium and having the same in the same horizontal level. So let's say since B and C are in the same liquid, and indeed this liquid is given by water at equilibrium, as they mentioned this in the text. and in the same horizontal level. Then B and C are submitted to the same pressure, and this means that the pressure at the point B is equal to the pressure at the point C. And now in part B, deduce then the value of the pressure of the confined gas. So by deduce, it means that we need to use the previous part. In the previous part, we have determined an equality between the pressures at the point B and the point C. We have that PB is equal to PC. So what does the pressure of the confined represent? It is the pressure at the point B, because whenever we are interested in determining the pressure, we always look upward. So notice that B here is submitted to the confined gas. In other words, it is submitted to the pressure due to this confined gas. So we are interested in determining the value of PB. So let's say first B is submitted to the pressure of the confined gas. So they usually give half a mark for this statement. So if we determine the value of the pressure at the point B, then we have determined the pressure of the confined gas. But we know that PB is equal to PC, and we have already determined the value of PC. So but PC is equal to 104,360 Pascal. Then in this case, the pressure at the point B is given by 104,360 Pascal. So the pressure of the confined gas is given by this value. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.